All right. Hey, everybody. So today we are doing an intro to neural networks, part 1 of 3 of our neural network series. And today we're just going to go over how or what is a neural network, first of all, and then we're going to walk through an implementation of a neural network. Now, this notebook itself doesn't have implementation. This is the notebook that you have on the repo as well. I think there's no code in this notebook. However, linked on this notebook is a Colab notebook. So I don't know if you all have seen this yet. I don't think so. I haven't shown you all this, but if you've come across it, maybe you've seen it. But Google Colab is basically Google's version of a Jupyter notebook. And it's pretty useful, especially if you're running something big like neural networks. I'm going to walk through how this works in a little bit as well. But for your projects, if you find that your computer is just really slow, looking to Google Colab can be an option. And the way that you work with your data on Google Colab, all you have to do is upload all of their data files or whatever your data files are onto your Google Drive, and it can actually connect with your Google Drive. So I'm going to show you all how that works later. But to start, we are getting to neural networks. So before we get into any of the details of neural networks, I first want to show you all that neural networks can exist in many different forms. Here's like a cheat sheet. I don't know why they call this a cheat sheet. I wouldn't say this is a cheat sheet, but this is a diagram of all the different kinds of neural networks that exist in the world. And I don't even think this list is exhaustive, but there are a lot of neural networks that exist. Out of these, the ones that we're going to see, today we're actually going to start with the simplest form of a neural network, which is a perceptron. And perceptrons, when we see how a perceptron works, we're going to see that that's actually pretty similar to something that we already know. It's actually very similar to logistic regression. And a perceptron is basically the building block of most neural networks. So from a neural network, later today, we're going to see a deep feed-forward network. Also, things that we're going to see within the week, we'll talk about recurrent neural networks and LSTMs. Now, these I'll save. These are going to be what we talk about on Thursday, and this is basically the neural network for time series. So if you're thinking of doing time series in the future, or even for this project, these will be the neural networks we look at. What else? And there's one more that I want to find. Convolute here, or is there a regular convolutional neural network? Okay, this is deep convolutional network, which is also what we're going to work with. Deep convolutional networks or convolutional neural networks, you might see the acronym CNN. That's the one that is more used for image processing. So for those of you who's working on that image classification project, very likely you'll be using deep convolutional networks, and I will talk about that. I keep forgetting whether I talk about it tomorrow or Thursday, but I think it's tomorrow. But yeah, there's a lot of networks that exist. SVMs, to some extent, when you use the kernel trick, it can be very, very similar to a neural network, which is why sometimes it's classified as so. But yeah, autoencoders. Autoencoders are what make word embeddings. That's what we talked about last week. That's also a neural network. I'm not going to talk about GRUs. GRUs are another kind of neural network that are used for time series data as well. But yeah, so many different kinds of neural networks. I personally have not seen like half of these in my own work. So yeah, just wanted to show you all that neural networks exist in many, many different forms. All of these considered neural networks. All right, so first to start, when we move on to deep learning, this is kind of funny. I follow like a meme page on machine learning. When you move on to deep learning, you'll see that very often it tends to outperform any of the models that we talked about back in phase 2 or even earlier this phase. It does outperform a lot of things because of the, because of its complexity. And we'll see what that means. Some quick applications of neural networks. Clustering, you can do clustering with neural networks, actually very, very similar to how we were doing clustering before. I'm not going to go into this today or during this week, but depending on what your capstones look like, I might talk about it. For pattern recognition, when we talk about images, pattern recognition is going to be very, very relevant. So we'll talk about that more tomorrow. Image recognition, same. Time series forecasting, as I mentioned, a recurrent neural network or an LSTM or a GRU used for time series forecasting, and also for image generation. Deepfake technology is, again, deepfake technology is built on top of GANs, which stands for Generative Adversarial Networks. We're not going to get into that at all because it's a little bit out of the data science scope. It becomes more of like, machine learning for, I guess, creating things like that. Not really in the realm of analysis, but super, super cool that those are also built off of neural networks. Some limitations of neural networks, though, they're very good for prediction. You'll see that neural networks have very high predictive power. As I said, it does outperform a lot of the models that we've talked about so far. However, very bad for inference. The fact that we were able to look at our models from the last phase and look at feature importances, take a look at coefficients, figure out why things are being classified or regressed a certain way. You can't do that with a neural network, and we'll see why in a little bit as well. Also, very computationally expensive. One reason why, instead of running my neural network on Jupyter Notebook, I decided to put it on a Google Colab Notebook, which again, I'll go over more details about this later, is because it's very computationally expensive. I don't know if any of you here has already experienced their Jupyter Notebook kernel dying on them. If you worked with a very large data set this last phase, which I don't think many of you have, but this phase actually very likely, like if your text data is of too high dimensionality, or if you just have too many rows, if you're like pushing like 6-digit number of rows, you might run into some of those issues. So completely fine to migrate any of your work over to a Google Colab Notebook, and I'll show you all how to do that over the week as well. Cool. Any questions before we start diving into technical details? All right, so as I mentioned at the very start, the building block of a neural network, of most neural networks, is called a perceptron. And to compare a perceptron to something that we already know, perceptron actually works very similarly to a logistic regression model, which we learned at the start of the last phase. So let's just think about one row of data to start, just one row of data. And we'll talk about how this perceptron is trained and how it learns how to classify things. So this is what, we haven't really represented our information like this yet, but this is one way that we can think about logistic regression. We have our inputs for each feature. So let's just say our data set has 10 features. You're gonna have 10 of these input nodes, one for each feature. So maybe you're doing our churn data set, and then you have our 10 different features that can be used to predict churn, things like customer service calls or amount of minutes used. Each feature will go into a single input node. And as we know how logistic regression works, it is a linear combination of these features. So through here, you'll feed in your input, multiply it by some weight, and sum it all together. So you're going to sum, actually similar to linear regression as well, we're going to sum the value of the feature plus the weight that has been learned by the model, add a bias, and the bias is basically your intercept term, and run it through some activation function before predicting churn or not churn. Now, this activation function for something like logistic regression is just, is this value above or below 0.5? That can be your activation function, right? Because if your value is above 0.5, it's going to round up to 1. If it's below 0.5, it's going to round down to 0. Tomorrow, we're going to do a little bit more exploration on what activation function means, because activation functions can exist in many different forms. But this is how you can think of a logistic regression, right? You have your inputs, multiply by their weights, add an intercept term, move it through that, like, is it greater or lower than 0.5, and you get your logistic regression classification. So any questions here? So as you can see here, weights are determined through gradient descent. We had talked about this before. The bias term is our logistic regression intercept term. Activation function is the sigmoid function that forces output values between 0 and 1. And the output is our classification result. So questions about this representation of something that we've already talked about before. You can also think of this as regression as well, where the activation function can literally be like nothing. It can just be take the value as it is, and you will output like your housing price, for example. Cool. All right. So the perceptron algorithm is about learning the weights for inputs in order to draw a linear decision boundary that allows us to discriminate between two linearly separable classes. So each perceptron is trying to draw a linear decision boundary, which is actually quite similar to what logistic regression was doing. So again, this is just another way to explain what we did before. It takes an input, sorry, let me zoom in, I realize this could be quite small. Takes an input, sums them up with weights, adds a bias, applies some activation function to get your output. Now, again, you can have different activation functions. We'll talk more about that tomorrow. And basically, many perceptrons put together are going to create a neural network. So the simplest form of a neural network is literally like logistic regression or linear regression. But you're doing a lot of these layered on top of each other, and that forms our neural network. Okay, so linear decision boundary, that's just an example of what that looks like. Questions about this before we start to scale up? Okay. Oh, by the way, before I get any more into this, in terms of expectations of how much you understand of neural networks, so what we've talked about so far up to this point, before we got into any neural networks, that is machine learning. And machine learning is like a field on its own. From neural networks onwards, that's the field of deep learning, which is also a subset of machine learning, but deep learning is like a whole nother beast. So typically out of bootcamp, most students don't end up using deep learning in their first roles, but you can build up to it. So there is usually not a very high expectation of understanding how all neural networks work, because that's a lot. I think for the most part, understanding the perceptron and how the perceptron works, which, as we know from this, very similar to the linear models that we've talked about before. And also like very high level structures of how different neural networks work. So we'll get more into those once we get to those examples. But I just want to set the tone for like, you're not expected to hard code a neural network. That will never be asked of you. Okay. So multi-layer perceptrons. Well, perceptrons are linear. We have to go deeper, right? Like what's the point of having a linear decision boundary like this created by a neural network? Because we can get a boundary like this with some of the machine learning models that we've already created. So why do we stop here? We move on to multi-layer perceptrons. Basically, how do we build perceptrons on top of perceptrons? A neural network is powerful because it's able to really get into the nitty-gritty of decision boundaries, right? Like none of the models that we've talked about so far can get a decision boundary like this. The fact that this is a completely different section than this is not something that our models can do. I mean, maybe a decision tree to some extent, but you do run the risk of overfitting a lot. And actually overfitting does tend to be one of the things that you have to check for a neural network because of this reason. But neural networks can get you this very, very granular, very fitted decision boundary. So what do? We have multiple perceptrons and we have multiple layers. So first you have our input layer, and our input layer, again, will match the number of features that we have. Now, each of these is a perceptron. So this part I know can look a little bit confusing, but each of these is one feature. So X1 is a feature. Let's say this is like number of minutes. X2 is another feature, number of customer service calls. This is like international plan. And these inputs will go into each perceptron. So in this case, we have 4 different perceptrons going on, and each one is going to have their own set of weights and set of biases that will then get put into some activation function for each one, get aggregated into some output layer. So you're basically doing the same thing across these 4 perceptrons before aggregating your classification outcome. So each node in the hidden layer, as I just said, works like a single perceptron. Each node assigns different weights and biases to every row's inputs. Then each node, so each one of these has their own transformation, their own linear summation, and their own adding of their biases, and also going through the same activation function before aggregating to get your final output. So yeah, any questions about just structurally what's happening here? Cool. One thing that you may be thinking about, if every perceptron is structured the same way, if each of these are doing this same process, wouldn't it just be 4 times of the same thing? No, so that's not what's going to happen because we actually instantiate the weights of each node to be slightly different. So that's how you don't end up with like 4 of the exact same perceptron that just gives you the same result, because that's not very helpful. What happens is when you're initializing each differently, the gradient descent processes will get so granular, and there are so many, like here, instead of having like, if you had 10 features, instead of having 10 parameters or 11 parameters to adjust, you now have 11 times 4 parameters to adjust, and they're all optimizing together with each other. Cool. So very quickly about activation functions. Depending on the task for your neural network, you might want to choose a different activation function. Now, here I'm just listing the activation functions that you can use for classification problems. Tomorrow, I'm going to go more in depth into some other activation functions that you could use for things like creating word embeddings, creating a regression model. If you want to do multi-class classification, there are other functions for that. But these are mainly the activation functions for classification because the output values are usually between 0 and 1, so that you can just round to 0 or 1. Cool. So for the output layer, experimentally, what has been shown is most cases ReLU, which stands for, oh shoot, what does ReLU stand for? It stands for, oh my gosh, I'm gonna Google this super quick. ReLU stands for rectified linear unit. Okay, and we'll talk more about what that means tomorrow, but ReLU is usually the most common one. Softmax activation is good for multi-class problems, and then sigmoid for binary classification problems. Now, activation functions are actually used at different parts of our neural network, and we'll talk about that later on as well. Okay, so this is the tough part. Backpropagation is basically gradient descent for neural networks. It's pretty much the same thing, but because it's done at a much larger scale than, for example, we use linear regression to talk about gradient descent. Because it's done at such a large scale, I guess it has a different name, but it's pretty much gradient descent, but for a neural network. So if someone asks you about what backpropagation is, it's basically how a neural network learns versus, gradient descent is how a machine learning model learns. So backpropagation is the process of picking the optimal weights for any forward feeding neural network. Now, it's important to say forward feeding. We're not going to see, actually, aside from recurrent neural networks, most of the neural networks that we're going to see are forward-feeding neural networks because the data just gets passed from your input layer to your hidden layer to your output layer. Some other neural networks, actually from here, we can see that if we take a look at recurrent neural networks, which is the time series one, you see how there's this little loop that loops back. That just means that that kind of neural network is not purely forward feeding because in a recurrent neural network, it's taking into account the sequence of things. Like in time series, the sequence matters. So that's why that kind of loops back. So that is not a forward feeding neural network. But for forward feeding neural networks, it learns through the process of backpropagation. And yeah, it is a procedure that uses gradient descent to propagate error terms backwards. So earlier I talked about in this example how each hidden layer, each node in the hidden layer is a perceptron. You can have as many perceptrons as you want per hidden layer, and you can also have multiple hidden layers. Now, it is this addition of perceptrons through the same layer or through multiple layers that can give you a very, very non-linear decision boundary. Okay, so basically what's happening is you have your training data, you feed it through your entire neural network, and you look at your error. You basically look at your error term and see, okay, how bad is my neural network doing? Based on that, because there's so many layers of calculation that your data has to go through, this error term is actually propagated backwards. So let's just say at your output layer, you're at 50% accuracy for a binary classification problem. Not very good. 50% accuracy is pretty much as good as like guessing randomly if this is a perfectly balanced data set. So you have 50% error at the very, very end. What you then do is say, okay, based on this error, let's look one step back and figure out, all right, if we go back, where did these errors come from? based on this, and let's just say we have 2 hidden layers here, 2 layers of perceptrons. So let's just say, okay, here, 50% accuracy. Let's look backwards and see, all right, what's our accuracy value here? Or what is causing our low accuracy value there? And it's just going to keep propagating the errors back through the layers to readjust the weights backwards. So is back propagation just because these errors are being, it's sort of like a look back, figure out what we did wrong to adjust the weights. Cool. We're not going to get into the math of this during any of our study groups, but StatQuest has a really, really good like 5-part video series on the math of back propagation, which is quite, it can get pretty dense. But yeah, if you're really interested in neural networks, highly recommend it. Okay. So let's talk about gradient descent in neural networks. So neural networks are implemented at scale with large sets of data. Therefore, optimizing for speed becomes a big concern. Gradient descent can take a very, very long time to run if we're using a single training example every time to update the weights and biases. Therefore, we usually use batches of data to train our weights. So imagine if we had like a 10,000 row data set. The way a neural network would, I guess, by default train, it'll actually look at every single data point separately to see, okay, with its current weights, will it get classified correctly? Will it get classified correctly or not? So because that's not very efficient, because you're taking a single data point going through all of them at once, you can do this updating in batches. And so that's what batch and epochs are all about. So first, there are batches and there are epochs. These are 2 different scales of how you group things. So in batch gradient descent, you are going to pass all of the training examples through the forward propagation stage before using back propagation to compute the weights and biases. So that's kind of like what I was describing before. You have 10,000 data points, you put them all through a neural network, and at the very end, you say, all right, well, I got 5,000 correct, 5,000 wrong, we'll recorrect for that. So that is batch gradient descent. You'll see that in our example later, you can also do mini batches. So let's say we have 10,000 data points. What you can do is say, all right, instead of doing like all at once, and I do want to see some updates within this batch, I can do, let's say, 100 data points at a time, and then only update my weights every 100 data points rather than waiting for all 10,000 to go through. Depending on the amount of data that you have and how complicated or complex your neural network is, you can definitely play around with those numbers, and I'll show you all how to do that. Next, there's epochs. So an epoch is when you're done passing all training examples through the forward propagation. So this is kind of similar to when we were talking about recommendation engines. You know how when we were updating our weights, you can basically go back to the first thing that you updated and re-optimize again. That's what running multiple epochs is for. And usually for a neural network, because you want to get that very nonlinear, extremely fitted decision boundary, you can feed the same data point into your neural network multiple times. In my example later, I actually have each data point going through the neural network, I think 300 times is what I set it for. And you can see that at some point, it really starts to learn the patterns of your data. And I think it'll make more sense when we go through examples. But basically, batches is when you take subsets of your data at a time, put them through a neural network. Epochs is you tell your model how many epochs you want it to run. If you want to run 1 epoch, means it's just going to run all of your data through your neural network once. If you want to run like 5 epochs, it's going to do it 5 times. 1,000 times. 1,000 epochs means you're running each data point through a neural network 1,000 times, and each time it's going to keep learning and keep fitting to the data that you're feeding it. Cool. So there's also different kinds of gradient descent that is being done. So for example, the most common one I think is stochastic gradient descent, because it calculates error and updates the weight after each training observation in the training set. So that's, I think, the default, where it will just update it with every new data point. Next, there's batch gradient descent, which calculates error after each example, but only updates weight after all the observations in each batch has been trained. Then there's mini batch, which is kind of like in between. It splits the training example to mini batches, calculates error, and updates the weight after each iteration of the mini batches is done training. So it's kind of like a middle ground. Stochastic gradient descent is every single point. Batch gradient descent does it after all the training examples are done. Mini batch is, when you're defining smaller subsets of your data at a time. Cool. Next, we have random initialization. This is what I kind of talked about before. How do you stop each perceptron from giving you the exact same output? You start with random initialization. So when we feed no values forward through layers, we initialize them to be 0, but we do not, hold on. Yeah, so we initialize weights, there we go, weights with random values and biases to be 0. So we don't initialize weights to be 0 because all the weights will end up being the same, right? If everything starts at 0, when you do the gradient descent, they'll all descend the gradient the same way. And then, so you don't want to do that. So you actually start with some random initial values. You also don't want very large initial weights because that will saturate value of the activation function, but that we'll talk more about when we talk about activation functions. Okay. Before we get into implementation, I'm going to talk about some of like how all of these things that I just talked about kind of fit in. Any questions? Okay. I'm very aware that this is like a lot and it can be quite dense. But yeah, just understand that like deep learning is like another like its own college course a lot of the time. So it's okay. We only get like a shallow understanding by the end of this week. All right. So what we're going to do is we're going to run Keras on Google Colab. So as I mentioned before at the start of this, Google Colab is Google's version of like an online Jupyter notebook, which you can definitely use for all of your projects going forward, even if you're not doing neural networks. And Keras is the library that we're going to perform or we're going to implement our neural networks with. So Keras is built upon TensorFlow. So you might have heard of TensorFlow. It's basically Google created TensorFlow, the library for neural networks. And Keras is sort of like how we can make use of TensorFlow a little bit more. It's a bit more user-friendly than TensorFlow itself. It's sort of like Seaborn and Matplotlib. Keras is to Seaborn what TensorFlow is to Matplotlib. So it's made it a little bit easier to use. So yeah, it's the default for beginners because it's very user-friendly and easy to implement. So when you're building your neural network, some things to think about. First, specify the architecture. And we'll get more and more used to architecture. And it's really, at this point, a lot of experimentation because it's so complex. It's very, very hard to say, okay, I know immediately what I want my neural network to look like. You're going to see it's going to be a lot of trial and error. How many layers, how many nodes and hidden layers, what activation functions should you use? We'll talk about this. Tomorrow, we're going to talk about just tuning neural networks as well. So yeah, then you're going to compile your model where you specify your cost function and details about how to optimize. Things like learning rate comes back into play, optimizers, what kind of metrics you want to use. Then you're going to fit your model and make predictions. So this part, very, very similar to what we've already been doing. I've also linked some documentation here. Before I get into the Google Colab Notebook, I do want to show you all a couple resources for understanding the math of neural networks. Unfortunately, 1 week is definitely not enough to get into like the theory of neural networks. So I've linked these playlists over here. All right, so this is, hold on, let me just reconnect this. This is Google Colab. What's really nice about Google Colab is you actually have free access to some of their GPUs and TPUs for much faster processing. So where you do that is if you just go to colab.research.google.com and you can set up your own Jupyter Colab notebook. And under runtime, you can change the runtime type and choose what kind of accelerator you want. So you can use a GPU, you can use a TPU. If you pay for it, you can see over here that there are some limits to the space. So can I see what that is? There we go. You can see that I'm using 1.8 gigs of RAM and 0.16 gigs of GPU. If you want to use more, you can actually pay for it, but please don't pay for it if you don't have to. But just in case, you know that you have this as a resource. I know if you like sign up for some Google products, they give you some free credit to use on this, which I have seen some students do, but that's not necessary. I'm not going to ask you all to do something that you have to pay for, but just in case. The way that this works is pretty much exactly the same as Jupyter Notebook. What's annoying is the shortcuts are not the same. Like I personally, because I don't use this very much, haven't figured out a lot of the shortcuts, but main things to note, Shift Enter is still how you run code. So if you want to access data, so in this notebook, I'm not actually using a CSV or anything. I'm actually pulling data straight from GitHub. But if you wanted to access your data, you just have to mount your Google Drive, mount this onto your Google Drive. So the code is literally these two lines over here. Basically what will happen, because I already ran this earlier today, what will happen is there will be a URL for you to log into your Google account, and they'll give you like this code that you just copy and paste in there, and you can access your Google Drive. You can actually like CD and like LS through your Google Drive to find your data file, which is really cool. All right. So what we're going to do today, we're going to use Keras, and we're going to use a bunch of different things through Keras that I'm going to talk about once we get there. But we're also going to use our trusty pandas NumPy train test that we know as well. So we're going to run this. And this is the data set that we're going to use. We're going to use the Pima Indians data set. It's not very big, just because I want this to run very quickly. So this is only 768 rows, 9 columns. So same as what we've been doing before, I'm just going to do my train test split over here. And you can see my train is 514 rows. My test is about, I think, about 200. Cool. So first, let's talk about defining the structure of our neural network. As you get more and more used to coding out neural networks, this will slowly get more and more familiar. But you always start with instantiating a model. And that's what we've been doing with scikit-learn as well. And just from here, we're instantiating a sequential model. Now it has to be a sequential model. They actually have a lot of other kinds of models. Like as you see here, there's all sorts of different kinds of models, but we're doing a sequential model because our data is just going to go through the list of layers. So for our purposes, I think everyone should be using a sequential model, unless you're doing some really high advanced time series stuff, which you shouldn't be at this point, but we can talk about it at the capstone if you do decide to do a different kind of model. Cool. So first we're going to add our layers. So first you can see that we have our first hidden layer. And actually, first let me show you that sequential is something that you import from models. And then for layers, you can import dense. Dropout I'm going to talk about tomorrow. I think activation I'm talking about tomorrow as well. But anyways, first we have our sequential model that we've instantiated. For our first layer, whatever the first layer is, for our purposes, we only know dense layers right now. Basically, a dense layer is just a layer of perceptrons. 12 means there are 12 nodes. So there are going to be 12 perceptrons here. For whatever the first layer is, you have to give it your input dimension. So our input dimension is how many features we have. And for this data set, we have 8 features. So we have to tell it that the input is 8. And the activation function is ReLU. So every hidden layer, every layer actually has an activation function. And by default, you usually start with ReLU. I'm actually going to show you all a grid search version of grid search for neural networks on Thursday. So be ready for that. Cool. For our purposes, let's just add another hidden layer to see how it helps. And for additional layers, you just have to say how many nodes you want and the activation function. So that's there. So we have 2 hidden layers in this neural network. What that means is it will look like pretty much like this one. These are our inputs, and we're going to have 2 hidden layers, and we're going to get some output here. The orange will be the output. Then at the end, we just have to compile our model. And we compile our model by giving it a loss function, optimizer, and what metrics you want it to optimize based on. So metrics, what you want it to optimize on, that's pretty straightforward. You want it to optimize on accuracy. Optimizers, we'll talk about it tomorrow, but it's basically what is the gradient descent process you want it to take. Atom is actually currently one of the highest performing optimizers, so most of the time you can just use that. Next, to talk about output layers, for an output layer, because we're doing binary classification, we only need one output node. Now that one output node, if you think about it, if we have a sigmoid activation function, you will either get a value of 0 or 1. Because if you think about it, this last step, after aggregating things from the last 2 hidden layers, you're going to force it through a sigmoid function, which is what we did with logistic regression as well. We forced our output through a sigmoid function, force it between 0 and 1, and then just round off our values to do our classification. And we only need one output node. Now, if you had a multi-class problem, you would actually turn this into, let's say you had 3 classes, you would actually turn this into 3, and then you would have a different activation function. Now, this loss function is very similar to what we had. It's literally our cost function for gradient descent. So right now, this loss function is binary cross entropy. Depending on what kind of task you're doing, you might want to have different loss functions, but binary cross entropy is usually the loss function that you use if you're doing binary classification. If you're doing multi-class problems, there is, what's the other one? I think I mentioned it a little bit earlier. It is softmax activation function. There you go. Tomorrow we'll go through a whole list of these as well. All right, so now that we've defined this model, let me see if I defined it. Cool. I've defined this model with 2 hidden layers, 1 output layer, and then it's going to optimize based on binary cross entropy and accuracy. We can also take a look at our model summary. So model.summary, which model again is a variable that we instantiated sequential to. Model.summary will actually show you, 1, the kind of layers that you have, also the number of parameters. As you can see here, each layer has a good number of parameters, whereas before, if we had 8 features, you would have for logistic regression 9 parameters. But in this case, with only 8 features, we're already at 277 parameters. So you can imagine that linear relationship is already gone because each feature is going to be multiplied by a bunch of different weights before being summed together. And they're going to be summed together in different ways as well. So at this point, with this fairly simple small data set, we already are training 277 parameters, 277 values of weights and biases, or coefficients and intercept values. All right, so that's just the setting up of the model. To run your model, there's quite a, well, actually this is fairly straightforward too. You can see here, I'm saving the fitting step to history, and you'll see why in a little bit. But I'm just doing model.fit on my X train, Y train. Here, the number of epochs, the number of times that I want my neural network to see all of my data, I put 300. Verbose basically, if you change this to like 0, 1, 2, 3, it'll show you different amounts of information here. I'll run this in a little bit so you see what I mean. Batch size, meaning how many observations before something is updated. And then you have your validation data, basically like your test metrics. So when I run this, you'll see that this output's going to re-output itself. So cool. This training is going on. What do these numbers mean? So this is the very first epoch, and it's 6 out of 6 because I set my batch to be 100. And in this training set, I have 514 points. So it's actually doing 100 at a time. And then the last batch only has 14. So it's 6 batches altogether. So that's what 6 out of 6 is. And the first round, the loss is at 22. And the number of loss is kind of arbitrary to us. It's all relative. But our accuracy value is at 35%. And our test accuracy is at 34%, which I think is worse than random guessing at this point. But as you can see, as our neural network sees our data over and over again, it starts to improve over time. So this whole thing took 21 seconds to run. And over time, you can see that the numbers start to increase, right? Even at, let's go to see epoch number 100. At epoch number 100, we're already at an accuracy of 71, validation of 67.72, and it looks like it's starting to plateau out all the way when we get to 300. When we get to 300, we're at an accuracy of 74, validation of 70. So we can rest assured that our neural network has seen each data point like 300 times, and this is the state of the model as it is. So why I'm saving the history is because the history actually stores all of this information that's being output. So the reason why I set, I need to do the scrolling here. The reason why I set model.fit to a variable is so that I can plot these results. So over time, and this is something that you should analyze with a neural network as well, this is our loss function, and over time, great. Our loss is getting better. And our loss is literally computing binary cross entropy again, it's all relative. So you just have to see this like plateau, this plateauing happen. So this is our loss function, and this is our accuracy. You can see it's a little bit jaggedy, but that's also because that in our training set, we only have like 500 data points. In our test set, we have like 200. So it can be quite sensitive. But as you can see, it starts to plateau off. Typically, I would say that, all right, maybe I would have stopped training around like 100 epochs because it's starting to overfit. As you see, the red line is training, the blue line is testing, and a little bit of overfitting is happening. I mean, it's like 5%, depending on what your data set is and your business cases, you might want to evaluate differently, but this is definitely overfitting. But at this point, I would say, okay, maybe we can stop at 100. I would go back and change it to 100 epochs. I'll talk about some other things that you can do if you want to like tell your model to stop training at a certain point. We'll talk about those later this week. But yeah, just like that, we've run our very first neural network. At this point, any questions? Cool. So neural networks are very dense. I think that if you do want to incorporate a neural network in any part of your portfolio, I do think that this project is a good opportunity to do that because it's harder to interpret and connect things to a business case with a neural network. But yeah, we can definitely discuss that like 101s or whatever. Cool. Awesome. Well, for the rest of this week, next week, we're going to talk about more tuning of neural networks. We're also going to talk about specifically images and how those work. I believe I'm talking about that tomorrow. And then on Thursday, I'll talk about time series applications of neural networks too. Nice. All right. Any final questions before we close out for the day? Going once, go twice. All right. Well, if there's anything y'all need from me, Slack me and let me know. Please, if I've slacked you to ask you what your phase 4 project is, it's because you hadn't responded on the poll. So let me know. I do want to get these project pairs out by the end of today so y'all can start working. And if for whatever reason, like next week is not a good week for you to like be collaborative with someone else, let me know as well, because I will definitely take that into account and then you can, yeah, do that. Sweet. Cool. Any other questions? Let me know. Look out for your project pairs. I will Slack them out later today. Cool. Well, if there's nothing else, you all have a good rest of your day, and I look forward to more neural networks for the rest of the week. Bye, everybody.